Hello and welcome to another digital design class. In the previous class, we started with combinational logic circuits. We went through half adders, full adders, and decoders. Today, we will continue with combinational logic circuits, and we will go through encoders, multiplexers, and how to solve some problems using multiplexers and encoders. So we learned that a decoder, as its name stands, it extracts information from the code. In a decoder, we have n inputs and we have 2 and a power of n outputs. Some decoders have an extra pin, which is called the enable pin or the enable control pin. And by activating that enable pin, the decoder starts working. By deactivating, meaning when we give it a 0, the decoder stops working. Now, using these decoders that have enable control, we can expand the decoder and, for example, use two 2x4 or 2 to 4 decoders and build a 3x8 decoder. We also mentioned about the different types of decoders. Some of them are active high, some of them are active low, meaning when they are active, the output that is activated is going to be 1 when it's active high. When it's active low, that output would be 0 and the rest of it would be 1. And the only difference between them, as you can see, is we show it with a knot or a circle at the output. So decoders can be used sometimes to implement other type of combinational logic gates to produce them. For example, using a decoder, we can create a full adder. A full adder from a decoder will look like this. We would have 2 OR gates connected to the outputs. And in this example, each output is a minterm. All minterms are produced, and the sum is the required minterm. And for this example, SXYZ is going to be the summation of 1 to 4, 7. And the carry C of XYZ is going to be the summation of 3, 5, 6, and 7. So again, we can build a full adder, and I'll explain, give more examples about using these type of complementary, these type of logic circuits to build other type of logic circuits in general. And I'll give you some examples from decoders, encoders, and multiplexers as well. Now, we can do the same thing using an active low decoder. So on the right, you can see an active low decoder, and on the left, you can see an active high decoder, for example. And again, create the full adder using a 3x8 decoder. Now, the next type of combinational logic circuit that we have is called the encoder. And the encoder is the opposite of the decoder. So we put information into code and we create a binary encoder. In a binary encoder, we would have 2 and a power of n inputs, and we would have n outputs. So input, output. So if we have 4 inputs, we would have 2 outputs. If we have 8 inputs, how many outputs would we have? 3 because 2 in the power of 3. So we would have 3 outputs. 16 is going to be 4. 32, 5, and so on. So we have 2 in the power of n inputs and n outputs. For decoder, we had n inputs and 2 in the power of n outputs. Now, this is an example of a 4 to 2 binary encoder. We have actually drawn 3 of them, and we can add a 4th one, obviously, as well. And here, if x1, x2, x3 is 0, 0, 0, y1, y0 would be 0, 0. And here we can actually add another one. I'm going to call this x0. And here, x0 could be 1. So when we have 0, 0, 0, 1, it's going to be equal to y0, y1 would be 0, 0. Then if it's 0, 0, 1, we're going to have 0, 1. And then it's 0, 1, 0, we're going to have 1, 0. And when it's 1, 0, 0, we're going to have 1, 0, 0, 0, we're going to have 1, 1. So this would be equal to x0 technically. This is equal to x1. This is equal to x2. And this is equal to x3. 1, 1 is 3. 1, 0 is 2. 1 and 0. Okay. So again, an encoder is a device that puts information into a code. For an encoder, we have 2 in the power of n inputs and n outputs. And it's the same as a decoder. We can have an active high or active low encoder as well. This is an expanded octal to binary encoder. In other words, it's an 8 to 3 encoder. 2 in the power of 3 gives us 8. So 8 to 3. Now, here, if I0 is 1 and I1, I2, I3, 4, 5, 6, and 7 are 0, then Y0, Y1, Y2 would be equal to 0 because it's equal to 0. So this is equal to I0. This is equal to I1, 0, 0, 1. 0, 1, 0 is equal to I2 because it's equal to 2. 0, 1, 1 is equal to I3. 1, 0, 0 is equal to I4. 1, 0, 1, which is 5, equal to I5. 1, 1, 0 is I6, and 1, 1, 1 is equal to 7, therefore I7. So a good way to memorize it, just convert this to decimal. So 1, 1, 1 is equal to 7. So we know that I7 goes to the output. And or in other words, Y0, Y1, Y2 would be I7 when I7 is activated. So how does this work? Here, if this is 1 and the rest is 0, then the output would be what? Would be 1, 1, 1. Okay. If all of it is 0, let me give you an example. If all of these are 0, let me do this one. And I4 is 1, what would the output be? So I0, I1, I2, and I3 are 0, 0, 0. I4 is 1, and I5, I6, and I7 are 0. What would my output be? What would Y0, Y1, and Y2 be? Perfect. 1, 0, 0, which is equal to what? So therefore, we know that I4 is activated. Okay, and the rest of it is. Now, let's do another one. What if this is also 0 and I6 is 1? What would the output be?
One, 1, 0.
Perfect. 1, 1, 0. Thank you so much. Now, what if I6 and I2 are both 1? What happens here? this would not produce any results because you're going to have an interfere between the inputs. Only one of the inputs could be 1 at each time, or in a low active situation could be 0. So only one could be different. You can't make 2 of them or 3 of them different at the same time. So because of this, 2 of them being 1, you're not going to have any output. It's going to create error. Okay. So, and that's the reason sometimes you see in a binary encoder IC, you accidentally, don't properly ground one of the inputs. It has a little bit of voltage and the output is just, the LEDs are just flashing and changing. It's because of this. Don't have any solid answer. And again, we have for active low as well. So if this is 1, 1, 1, 1, 1, 0, 1, 1, what would the output be? Y2, Y1, Y0? Kind of 0, 1, 0. Because I2 is active and 0, 1, 0 is equal to I2. Okay. And this is for an active low situation. Okay. In active low, all of the zeros are ones and all of the ones are zeros. And you can easily just memorize this. So everything is 0 except everything is that it's on the diagonal. Okay, is it clear? Yes. Now, for an 8 to 3 encoder, the circuit is going to look like this. We're going to have 3 OR gates connected. The outputs are the 3 outputs, and we will have 8 inputs, I0 to I7. And we can easily extract Y0, Y1, Y2 from this table, same as we did last time. We can create a K-map and find Y1, Y2, Y0, all of that from the K-map, and then find this function, and using that, be able to easily extract extract the circuit and write down the circuit and design the circuit and analyze it. Now, another very good and useful application for an encoder-decoder pair is obviously for coding something, so but it's not a very sophisticated coding system. And there's another application, very good application. From what you see here, what is the benefit if I use a binary encoder and decoder? Why wouldn't I just directly connect the first key to the first LED and the second one to the second one, third one and third one, fourth, and so on? What is the benefit of using the encoder decoder? And if I do that, I actually get rid of the encoder and decoder and make it much simpler. So imagine I want to control some outputs, lights, using some keys. I have 8 keys and 8 lights. Okay. I can use a decoder encoder, or I could directly connect the lights to the switches. What is the benefit of using binary encoder or binary decoder in this system? Can you think of what benefits does this give us using the encoder-decoder pair? By the way, in this pair, if, for example, I5, this one is 1 and the rest is 0, meaning the switch number 5 is turned on and the rest of the switches are turned off, then 5 is going to be equal to 1, 0, 1. Am I correct? And again, here 1, 0, 1 translates to 5 being turned on and the rest of it being turned off. 7, 6, 4, 3, 2, 1, everything else is turned. Okay. So you can turn on one switch at a time. And actually that causes a problem as well. If we directly connected the LEDs to the switches, we could turn all of them to one at the same time or turn all off. But we use binary coders and decoders, encoders and decoders a lot actually in computer, especially in computer architecture and designing different systems. It's particularly useful when you use a bus system. The one main reason is to reduce the number of wires in a connection, okay? So for 8 to 3, you won't see a lot of complexity, but imagine if you had, let's say, a 32-bit or a 64, and 32, 64 it's very normal in a computer system. So 32, you would need 32 lines connecting between the input and the output, okay? And for 64, you need 64 of these. It's going to be a lot of wires. It's going to occupy a lot of space. But if I use an encoder-decoder pair, I can tune that to just 5 wire and 64 to just 6 and 128 to just 7 wires, okay? So less than 1/10 for 128. For 256, generally just 8 wires, okay? So it's going to significantly reduce the number of wires that we have. And that actually makes it more reliable because the possibility of one of wires cutting is high, but for a decoder encoder, you're going to have a lower possibility. And you can technically use a bus system, these 3 as a bus, and connect multiple decoders and encoders and the output to it. And obviously the other important part is to be able to code the system, but that's actually, we have better ways to do coding. This is a very primitive way and amateur way to do coding. But the main reason is to reduce the number of the wires between connection. And imagine if you want to connect to telephone, phone wires for 100 miles. Instead of having 300 wires, 400 wires, you can just use 8, 9 wires to do all the work, okay? Now, another type of combinational logic circuit that we have is called a multiplexer. So a multiplexer is like a gatekeeper, I could say. Imagine we have a 4-lane highway, and suddenly all those 4 lanes are merging into one, okay? What happens if all of them merge at the same time? They're going to crash, okay? So we have to come up with a system that is able to manage the input data, in this case, the cars coming in, and tell which car is allowed to pass. It's gonna be like a toll booth, and you're gonna have a 4-lane coming inside like a city, and the city has downtown just 1 lane. If you put all of them together, you're gonna have crashes, traffics. In the data, you're gonna have overlap with the data, and it's gonna destroy the data. So what you're gonna have, imagine this is a toll or a control, I would say, and this tells which one is going to go. So it could signal, for example, if this is number 1, 2, 3, and 4, and it could give a sequence. It would tell number 3 to pass first, then number 2, 1, then number 4. So depending on the priority. So you can pass number 3, then number 1, and number 4, and so on, okay? Based on the priority. Maybe number 3 is a fire truck, so it would tell fire truck to go first. Number 1 is the police, so police, fire truck. Number 2 is an ambulance, and number 4 is just a normal civilian car, okay? So you can, first of all, you can set priority on which one goes first, and you can have a control over the inputs as well. And to have that control, we have 2 pins. We call it the select pins. We show it with S0 and S1. And by selecting, so different numbers, we can select which input goes to the output. Now, for example, if S0, S1 is 0, 0, then I0, so let's call this I0, I1, I2, and I3. This is I3. My pen doesn't work on this side of the screen. I don't know why. I'm going to write it here, I3. And this is my output Y, okay? So if it's 0, 0, then I0 goes to the output. If it is, for example, 1, 1, then 1, 1 is equal to 3, so I3 would go to the output. So this is for 0, 0, and this is for 1, 1, okay? And it can't go both at the same time, just one. And we have a clock system. I explained what that does to prevent them from overlapping. So a multiplexer is to coordinate the input to the output. We would have multiple inputs and one output. So the multiplexer always has one output. It has 2 in the power of n inputs, and it will have n select. Okay. So in this particular case, we have 2 selects. So 2 and 2 in the power of 2 would be 4 inputs, and always it has one output. Okay. So what if we have 3 select points? We would have 8 inputs and again 1 output. We would always have one output, a single output. Now, another way I usually give this example as well. Imagine the class is over and everyone wants to get out of the door at the same time. You're going to have a jam. But if I stand in front of the door as a control system and I give each one of you a number and I say, okay, number 2, you can go out now, and then number 3, number 4, I'm going to be the select, you're going to be the inputs, and only one person could pass this door at a time. Okay. Now, what does this look like? This is exactly what happens in a computer when we want to convert parallel to serial. Okay. So if you have parallel data or parallel lines coming in and you want to make it serial, meaning if you have I0, I1, I2 coming all at the same time, but I want to put them in a line like serial to be I3, I1, I0, then I would use a multiplexer. So multiplexers are very good when you want to convert parallel to serial. Now, data. Parallel data coming in for 4, from 8, or 10, 100 lines, and then you want to convert it to serial. Now, where can we use this in electronics? You have a project working on Arduinos, and that Arduino has only one analog input, okay, A0, for example, for a Node MCU or the Arduino Uno. You have limited amount of inputs, okay, but you want to connect this input to 4 different sensors. You want to connect it to a temperature sensor, to a humidity sensor, to a light detecting sensor, and to a motion sensor, for example. Okay. One way is to go to another, like a larger Arduino, like the Arduino Mega, but most of the time, even Arduino Mega, if you have 20, 30 inputs, it's not going to solve your problem. So one thing that you can do is you can use a multiplexer and connect the select to the Arduino. You can code that from the outputs of the Arduino to select the inputs at an interval. So let's say in every 10 seconds, for the first second, I want to measure the input from sensor 1 or I0, the next 1 second from I1, and then I2 and I3. So what I would allocate, I would divide every second or every 10 seconds, and I would say first I1 comes in, then I2, then I3, then I4, and so on. This works perfectly when you want to measure, for example, temperature, because temperature is not moving very fast. So if you don't measure it every second, even every minute, it's not going to make a difference, okay? And for light sensor, it's the same, humidity, all of that is same. So technically what you can do, you can even connect 16 or 32 sensors to a single input. If you have 16 sensors, you can use a 16:1 or 16:1 multiplexer, and you would have 4 select points. You would connect that select points to the Arduino, and you can program the Arduino that would put a sequence on which inputs it want to get. Sometimes you can even do that on demand. So for example, the project that you're doing, which is IoT, you want to just call some variables, okay? You want to see in real time what the temperature is. You don't need to know what the humidity is. So the moment that you connect to that Arduino, it would select, for example, 1,1, and 1,1 is for I3, which is connected to the temperature sensor, okay? So you can select which one you want to connect. So this is a very good way to expand the number of inputs in an Arduino, okay? To convert parallel to serial. And that's actually the most efficient way to do that. Going from a very tiny, Arduino Node MCU or ESP32 to a huge Mega. It's first of all that Mega. It's going to consume much more power, going to be more expensive, and it's going to it's actually going to consume a lot of space as well. So you need to build a bigger packaging, a bigger battery. Everything is going to cost more. Instead of that, you can just have your ESP32 and a multiplexer. And you can do the same thing for the output as well. Imagine your Arduino has only 2 or 1 outputs, and you want to control 10 different lights using what we call a demultiplexer. So a demultiplexer is the opposite of a multiplexer. It has 1 input and 2 to the power of n outputs and n selects. You can select which output you want to turn on. For example, which light you want to turn on. You can control hundreds of lights by using just a single output and few select points. So you can multiply the outputs that you can control. So the simplest multiplexer that we have is the 2:1 multiplexer. And the encoders, we show it sometimes by 2:4 or something like that. For multiplexer, we say 2:1 or 4:1 or 8:1, for example. So it's going to be 8 inputs and 1 output. So a 2:1 multiplexer, you're going to have 2 inputs, a single output, and a select point. If the select is 0, I0 goes to the output. If the select is 1, then I1 is connected to the output. Okay. And then we have the 4:1 multiplexer. You're going to have, again, 4 inputs, 1 output, and n select points. Again, if you have 0, 0, I0 is connected to the output, I1, I2, and I3, all of them are in high impedance. I'm going to show it with Z, or sometimes we show it with HI. HI means it's in high impedance, or other words, it's open. And only I0 is connected to the output. Okay. And the frequency of these systems are sometimes so high. For example, in Arduino, the clock could go up to 400 kilohertz. So 400,000 times per second, you can select which input you want. And for most sensors, this is completely fine. You're gonna, as mentioned, we even deliberately put a interval between measuring temperature, because if I measure temperature every half a second, it's gonna drain my battery much faster. So what we do is usually we ask the Arduino to measure the temperature every minute or every 10 or every 20 minutes, because then it's going to go into sleep mode, and the battery, instead of lasting a day, it's going to last 2 months. Okay, and you don't need to have like 10 million temperature data, because the temperature doesn't change instantaneously. It takes like 5, 10, 20 minutes to change. Okay, so again, the frequency of changing this select point is pretty high. Now we can combine 2:1 multiplexers and create a quad 2:1 multiplexer. Or in other words, we can have a system that looks like this. Again, we can combine all 4. We're going to have a select and E, which is enable. We're going to have B0, B1, B2, and B3, and A0, A1, A2, and A3. But what we want here is we want to be able to control them separately, and therefore we can control the select and enable. And by controlling that, you can select which inputs, for example, goes to the output. And what we do is usually what we will tie all of these together. So we can tie all of these together without a gate, and we can have a single output Y. And for example, if let's say I have 0, 0, I would have B1 going to the output and so on. So we can combine these multiplexers as well. Now, the important part is this, which you're going to have probably a question on your FE exam as well from this. One of the examples that I would solve is actually from an FE exam, and you're going to have multiple questions from this on your upcoming exam as well. So we want to see how we can implement a Boolean function using a multiplexer. So imagine we have this function f of x, y, z is the sigma of 0, 1 through 1 and 3. So we're going to have m0, m1, and m3, the minterms, okay? Sum of minterms is going to be summation of 0, 1, 3. So the first thing we're going to do is we're going to draw the truth table and write all the possibilities. We're going to have 2 inputs. Therefore, we're going to have 4 possibilities. And f is going to be our output, which is going to be, again, 1 at m0, m1, and m3. Now we're given a multiplexer, and we are asked to implement this function using the multiplexer. Now, I want you to think on this for a few minutes. Then I would try. Then I would start solving it. How do you think I can implement this function, this truth table, into that multiplexer? And by the way, just a hint, y is our f or our output. Should I connect x and y to 0, S0, S1, or should I connect it to I0, I1, I2, and I3? So what I can do here, I can connect S0 and S1, the selects, to our inputs, x and y. So for example, if it's 0, 0, what would the output be? It's equal to I0, yes? And what is f for 0 equal to? It's equal to 1. So I can connect I0 to a 5-volt source, or to 1. I can do the same for I1 as well. When this is 0, 1, then F1 would be equal to I1. And what is F1 equal to? 1. And I can do the same for I2, and I can do the same for I3 as well. So now I can even make it easier. I can connect all of these together, and I can connect I3 with a NOT gate. So now I will connect this to a 5-volt or a 1. All the inputs would be 1. I2 would be equal to what? 0. Now, depending on what I select, I'm going to get the outputs and which going to match the truth table. Okay. This is an easy situation. I'm going to give you a more complex situation as well. So what we can do to implement using the multiplexer is to connect x and y directly to S0 and S1. And then we could give the outputs 1, 1, 0, 1 to the input. So it's going to be 1, 1, 0, 1. And yeah, that's it. I don't know why. Now that we did that, I want you to find and see how we can implement this Boolean function f of x, y, z. Sigma is 1, 2, 6, 7 using the multiplexer. So the previous time we had 2 inputs and 2 selects. Here we have 3 inputs. We have x, y, and z. And we're going to see how we can implement this using the multiplexer. By the way, previously at the beginning of the combinational logic circuits, we learned that we can implement these using logic gates and logic circuits. You remember we did a bunch of problems and solved it. But instead of doing it using a lot of logic circuits, we can do it with a single multiplexer. It's going to be much easier. But I want you to think on how we can do that and how I could actually connect these to implement it using the multiplexer. Okay, so the first thing we need to do is to reduce the number of inputs to only x and y. To do that, we have to reduce this, which is an 8 by 2. We have 8 rows and 2 columns. By 2 columns, I mean x, y, z, I will consider 1 column and f as 1 column. To only having 4 columns because I wanted to have 2 inputs. So I have to find a way to simplify this and combine this. So let's combine the first 2 rows. In the first 2 rows, what is the relation between f, x, y, and z? Yes. So what happened to x and y between the first column, first row and the second row? They stayed the same, yes. And what happened to z? It flipped. And what is the relation between z and f? They are the same. So x and y don't have, when they are 0, 0, they don't have any effect on f, but z determines what f is. So what I can do, I can combine x and y into one block, and I can say for the first 2 rows, f is equal to what? Z. Okay, so when x and y are 0, 0, f is equal to z. What about the second row? I'm sorry, second part or second block. In other words, 0, 1, 0, and 0, 1, 1, the third and the fourth column, the third and fourth row. What is the relation between? Yes. So again, x and y are 0, 1, 0, 1, and f is z naught, or the opposite of z. Okay. Is that clear? Yes. Again, what happens to the third row? I'm sorry, the third block, the row number 5 and 6. Again, X and Y, I can put it in the same block. And F is equal to what? 0. F is equal to 0. So regardless of what Z is, F is equal to 0. And the last part, F is equal to what? Yes, perfect. F is equal to 1. Now I can divide it into 4 inputs, 2 selects, and I0 is going to be Z. By the way, this is the 2 first ones are I0. Second one is I1. My pen doesn't work. Then I2 and I3. And the outputs is going to be Z, Z prime for I1, 0 for I2, and 1 for I3. Now that was the easy one. Let's solve it for this. So this, we wanted to do an implementation using multiplexer. And by the way, for the previous one, we can even make it easier as well. Let me go back. Instead of having this, I can connect this to a Z, connect the notch to the second one, and I can connect this to a 0 and with a notch to a 1. Okay. I can have 2 inputs, Z and 0, and 2 knots that connect them together. Even make it easier. Okay. Simpler. Now the second one, first student to solve this gets extra points on the next homework. I want you to put aside, I know you already have the notes. Please turn off the road notes. I want you to think on this. It's very important. It's going to be 3 or 4 questions in your final exam and in the next exam. And I want you to think on this and solve it. Again, it's going to be the same principle of the previous one, but instead of having 2, you have 3 select points. And you have, because you have 4 inputs, you have to simplify that to 3. And the Boolean function for this, f of a, b, c, d, is going to be the sigma of 1, 3, 4, 11, 12, 13, 14, and 15. So this means that f0 is 0, f1 is 1, 2 is 0, 3 is 1, 4 is 1, 5 is 0, 6 is 0, 7, 0, 8, 0, 9, 0, 10, 0, 11 is 1, 12 is 1, 13 is 1, 14 is 1, and 15 is 1. Okay. I think we also have, yeah. So the first thing you want to do, and by the way, in the exam, we don't give you the truth table. You're going to have just the function and this sum of minterms, or SOP, which here is the sigma of 1, 3, 4, 11, 12, 13, 14, 15. So here you have 3 selects, but you have 4 variables, and you have to reduce that 4 to 3. It's going to be exactly the same as the previous one. Okay, did you solve it? Nice, yes.
Just cut the B out of it.
You can combine ABC. Yes, combine ABC. Let's set it last time. So it's going to be 0, 0, 0, and then 0, 0, 1. So do it every 2 rows. Yeah. Okay, so what we can do is we can combine every 2 rows. Again, ABC is going to be 0, 0, 0, 0, 0, 0. And what is the relation between F and D here? F is equal to D. What about the next two? A, B, and C are 0, 0, 1. And what is the relation between F and D? Again, still F is equal to D. Now, the next 2 rows, A, B, C are 0, 1, 0, 0, 1, 0. And what is the relation between F and D? Yes, it's F is not D. D not. And the next 2 rows, again, A, B, C are the same. And F is equal to 0. Again, next 2 rows, F is equal to 0. The next 2 rows, F is going to be equal to D. Next 2 rows, F is going to be equal to 1. And the last 2 rows, F is going to be equal to 1. So S0, S1, S2 is going to be equal to ABC. And I0 is going to be D. I1 is going to be D. I2 is D prime. I3 is 0. I4 is 0. I5 is D. I6 is D. And I6 is 1 and I7 is 1. So I can tie I0, 1 and I5 together connected to D and connect that with a knot to I2. I can connect I3 and I4 and I6 and I7 together and then connect them all with a NOT gate. So I can do this and this, connect these two with a NOT gate to each other, connect this to 0. I can do this for this as well. This to a NOT gate, and again this to D, and all of that to D. So I can have 2 inputs technically, D and 0. So we can use 2 4-to-1 multiplexers to build a 8-to-1 multiplexer. And in this particular case, we're going to have, again, 8 inputs, 1 output, and 3 select points. And the way that we connect them, we connect S0, S1 of the first one to the second one. And the Ys are connected through a 2x1 or 2-to-1 multiplexers. And the output of that is going to be our output. And the S from that is going to be S2. So having 2 4-to-1 and 1 2-to-1 multiplexer, we can have a 8-to-1 multiplexer. And we can have a 16-to-1 multiplexer the same way. We can put like 2 8-to-1 multiplexer or 4 4-to-1 multiplexers. And for example, here, if S0, S1 is 0, 0, because the S0, S1s are both connected, then for both of them, it's going to select I0. And if S2 is 1, it's going to select I0 of this, which is I4. It's going to be I1, therefore IY would be I4. Now, the demultiplexer is the opposite of the multiplexer. You're going to have 1 input, n selects, and 2 in the power of n outputs. Again, 2 in the power of n outputs. You're going to have n selects. It selects, and you're going to have 1 input. Now, this is used to convert serial data into parallel data. And example that I gave you, again, it's going to be, for example, the output of a microcontroller like Arduino, and you want to control multiple devices with a single output, you can use a demultiplexer. And it's the opposite again of the multiplexer. So if S0 is 1 is 0, 0, then Y0 would be I. If it's 0, 1, 0, 0, 1, it's going to be Y1 is going to be I. If it's 1, 0, Y2 would be Y. And if it's 1, 1, Y3 would be I. So again, if it's, for example, 1, 0, then Y2 is connected to I. Let me do a different color. If it's 1, 1, then Y3 would be I, and the rest of it would be on high impedance. And at each time, only one of the inputs would be connected to the output. Now, the multiplexer, demultiplexer can again be used as a pair. And this is a fundamental of the bus systems in a computer. So for example, in a computer, a multiplexer is the memory, and the demultiplexer is the CPU. We want to transfer data from the memory to the CPU. Instead of having 128 lines, we can have 8 lines, 1 byte. And we can convert that 128 bits to just 1 byte and transfer it, for example. Or we can combine all of that and go from parallel to serial and then back to parallel. It's good if the speed of the system is adequate, but if you want to, for example, use it for a data center and you need to do parallel computing, it's better to do all the connections in parallel. Nowadays, we have these powerful switches, Cisco switches, which could move like 10 terabytes per second. They have very fast speed, and this connection between these two multiplexers is a fiber optic, so the frequency is unlimited. So you can go for extremely high frequencies and be able to control. And by the way, nowadays when we speak about an AI cluster, you may think it's a computer like this, a rack. It's not. Sometimes an AI cluster is a combination of 2 or 3 cloud centers. So one may be in DC, another one is in California. And when you run a prompt on ChatGPT, they connect to each other and run for, and do one hash of processing. So both of them are communicating, which are thousands of miles away, as one supercomputer, as one cloud system. So even they may not be in the same state. They may be different parts of the country or world, and all of that works at the same time because of the insane speeds that the fiber optic system has and the switches that we have. And obviously, you can't run 10,000 wires for 1,000 miles. You need to have a system that converts these parallel to serial, and we do that using these multiplexers. So it's a basics, I could say, of communication systems, wiring, and also the bus. In a computer system, you're going to see a lot of these multiplexers and demultiplexers. We can also pick the priority, which one we wanted to go first and where we wanted to go. So for example, if you're playing music and suddenly you want to run like your smart home, you can pause that for a second and run another information. Usually we don't do that. We have a cache to store that music. That's a different story, but we can select the priority as well. Same thing on your phone when you want to, your battery is low, you want to reduce the background apps, so you can do, that's done in different parts. It's done both in the bus side and multiplexer and the memory and the CPU, and there's a lot of things, but you can set the priority here as well. And what it does, again, it converts parallel data to serial to have just one line, and then converts it back to parallel. These two must be synchronized. Again, the reason is we don't want the data to come on the line Y and suddenly I for the second one doesn't accept it, and then the data would be ruined, okay? Or we want, for example, imagine x0, x1, x2 is sending one data, I0, and then sending another data immediately, I6, but I1 is just opened once. So the data, again, is going to be ruined. So we want them to be synchronized as well. That we do through a clock system. So a demultiplexer decoder can be actually connected, and we can build a demultiplexer using a decoder as well. And the way that we do it, the S0, S1 are connected to I0, I1, and we have the enable for the decoder. So binary decoder with the enable can work as a demultiplexer as well. And this is the way that we connect them. But here we have a little bit of a limitation on the output just could be one at each point. So a multiplexer can act like a decoder, and a binary decoder with the enable can act like a multiplexer as well. But we have specific ICs for demultiplexers and decoders. Now, the basis of all of these are, and how we build these multiplexers is a device called the tri-state buffer, or what we call the three-state gate. And this is how we build multiplexers and so on. So what is a three-state gate or a tri-state buffer? It is a buffer that has one input, it's called A, one output, Y, and one control, okay? If the control is 1, then the input and output are connected. In other words, this is closed, okay? So whatever you see in the input, it's going to be the exact same in the output because it's a buffer. But when C is equal to 0, I'm going to do that with red. So when C is equal to 0 means this is disconnected. So output is neither 1 or 0. Some people think because it's disconnected it's 0. No, it's neither 1 or 0. It's in high impedance. So it's not 0, it's not 1, it's nothing, okay? So we don't care about A in that scenario. Y is going to be in high impedance. It's like a gas or water valve. C is 1 means the valve is open, gas or water could pass. C is 0, you don't have anything. It's completely blocked. And here, we can have a tri-state inverter as well instead of a buffer. The only difference here is that, again, when C is 0, you're going to have Y in high impedance. When C is 1, then whatever you see in A, you're going to have the not in the Y, or in the inverter in the Y. So in this particular case, if C is 0, let me draw the truth table. We don't care about X, Y is high Z. If C is 1, A is 0, Y would be 1. If C is 1 and A is 1, Y would be 0. So A would be the opposite of Y. Now, two tri-state gates could be connected together, the outputs. And in this scenario, we would have 4 different possibilities. If C and D are 0, 0, then both of them would be in high impedance. Therefore, the output would be high Z. If C is 0 and D is 1, the output would be connected to B. And if C is 1 and D is 0, it's going to be A. So again, if this is 0, this is 1, this would be connected. If this is 1 and this is 0, A would be connected to Y. And if both of them are 0, this is going to be high impedance, this is going to be high impedance, so output would be high impedance or nothing. But when we have 1 for C and D, then both A and B would be in the output, which is going to ruin, and it's going to be not allowed because it's going to destroy the data. So what we can do to address this, we can connect C and D with a NOT gate because we want to avoid the high impedance situation and the situation when we are not allowed. Therefore, we want to make C and D opposite of each other, and the way to do that is to connect them with a NOT gate. In this scenario, y is equal to a if c is equal to 1, and y is equal to b is if c is equal to 0. Now, what does this look like to you? Perfect. This is a multiplexer. This is a 2-to-1 multiplexer. C is our select, and A and B are the inputs, and Y is the output. So this is going to be a 2-to-1 multiplexer. This is I0, this is I1, and C is our select, S. Now, we can use the same thing to create a 4-to-1 multiplexer. Here we use three tri-state buffer, and we connect it to a 2-to-4 decoder. Now, let's solve this for S11 and S00, and the enable is 1. So S00, S11 gives us 10, which is equal to what? Y2. So Y2 would be 1, and the rest of it would be what? 0. Because the rest are 0, all of them are in high impedance, so you're not going to connect any of them, and therefore I2 would be connected to output. So Y would be equal to I2. And using the 3-state buffer, we can build a 4-to-1 multiplexer. Okay. And we can do the same thing to create an 8-to-1 multiplexer and so on. For that, we need a 3x8 decoder. That's it for the combinational logic circuits. In the next class, we're going to start sequential logic circuits. Our exam, we decide to be the second week of November. Am I correct? Yes. So second week of November is going to be the exam. I'm going to post an announcement about that. The other thing is about your final project. As mentioned, your final project deadline is December 3rd. And for the final project, you just need to build a simple digital logic circuit. Anything that has a NOT, AND, NOR, XOR, any of these combinational logic gates, decoder, encoder, and multiplexer is acceptable. And I will post the directions and the instructions for the final project as well. Thank you so much, and I'll see you on Thursday. No, because